Alright, welcome. Let's work Algebra 2 Homework 7.2. So we're going to be solving a lot of polynomials. There's going to be a lot of complex solutions, I think, lots of use of I, and lots of use of the fundamental theorem of algebra. Okay, so find all the roots of the following polynomials. What we learned today is that for this fourth degree polynomial, we should be expecting 4 roots. Okay, I don't see this as factorable, so I'm going to probably have to try the rational root theorem. And so my possible rational roots, I'm going to just copy them in for you. Possible rational roots are going to be plus or minus 8, 4, 2, or 1, all divided by 1. Okay, so it's going to be an integer if it's going to be a rational root. I gotta assume it's going to be, right, if it's on your homework and there's no additional information given. So let's just try x equals 1, right? We know in my class we should always start by checking x equals 1. 1x to the 4, 1x to the 3, 2x to the 2, 4x, and negative 8. Okay, we're going to try 1, that would be 2, 4, 4 is 8, sure enough, there we go. And so, from this thing, I've got an x minus 1, and then from this here, I'm going to have 1x to the third, because I took a fourth degree polynomial and divided out 1 power, plus 2x squared plus 4x plus 8. And I think that's going to be factorable as well with group and factor. So I'm going to say x squared times x plus 2 plus 4 times x plus 2. And then I'm going to factor out that x plus 2. Wait, no. X minus 1, x plus 2. And then I'm left with an x squared plus 4. Okay, and if I'm looking for roots, I should have done this a lot earlier, but roots is going to be where this is equal to 0. Alright, now I've got it down to factors that I can solve all of them. Okay, so x minus 1 could equal 0, and that would give me x equals 1. Okay, x plus 2 could equal 0. That would give me x equals negative 2. Or I could have that other thing equal 0, x squared plus 4. I know in the past we'd said that kind of gave us no solution, but we're willing to have an open mind now. So this is x squared equals negative 4, x equals, don't forget when you take the square root of both sides of an equation, you're going to need to remember the plus or minus. Okay, the square root of negative 4, that's going to be 2i. Okay, so I've got x equals 2i and x equals negative 2i. Right, and so those would be the roots of that polynomial. Alright, here we've got another fourth degree polynomial, and it comes with a graph. Okay, so obviously I'm going to need to use that graph somehow, and so I think that's telling me that I should think about maybe x equals negative 1 and x equals negative 5 as numbers to potentially try in synthetic division. Right? Okay, negative 1 and negative 5 are both numbers that divide 45. Okay, so it feels reasonable. Okay, so I'm going to copy in the coefficients, 1x to the 4, 6x to the third, 14x to the 2, positive 54x, and positive 45. Okay, no missing terms. I'm going to divide in. I'm thinking I'm going to run negative 1 through there first. Because with negative 5, I don't know, I wouldn't want the numbers to get out of control. I mean, I know eventually it's going to have to come back to 45, but maybe I see how it would have gone fine either way. But 6 minus 1 is 5. 5 times negative 1 is negative 5. That's going to be 9. Oh, no. Okay. Well, good thing it came back. And that's going to be 45 multiplied by negative 1. That's negative 45. And that's 0. Oh, okay. Now, I would say that 1, 5, 9, and 45, that looks pretty factorable to me because of that, parallel relationship. 1 to 5 is the same as 9 to 45. But I'm going to keep going because I just, have the suspicion that negative 5 is also a root. Okay, so I'm going to set up for another synthetic division. And I just want to point out, because I don't know, I just graded the recent free responses on the test, that when people were like, you can only do this, you can only keep dividing if you've divided and the remainder is 0. Okay, I saw people getting something that was not 0 in the last and then continuing to divide, and that doesn't work. That's not something that we can do with synthetic division. Yeah, I just wanted to point that out. Okay, so I'm going to run -5 through here. Okay, that's going to be a 0. Again, that one's disappearing, but that's fine. 0 times -5 is 0. Go down there. 9 times -5 is -45. That's coming back 0. Great. Okay, so I know that from these two here, I'm getting an x minus -1 and an x minus -5. And then from these over here, I'm going to get 1x squared plus 0x plus 9. Okay, and if I'm looking for the roots, I need to set it equal to 0. Okay, I can get x equals -1 here, x equals -5 there, and then x squared plus 9. Let me work this off to the side a little bit. So if I've got x squared plus 9 equals 0, hopefully you're getting to the point where you can start to see this coming, what's going to happen with this. But if you can't, just keep, following the usual steps. Solve for x. Wait, no, I'm taking the square root of both sides, so I need to remove the plus minus. And so that would be the square root of 9 times the square root of -1, which is going to be 3 times I. So x is equal to 3i, and x is also equal to -3i would be kind of the two solutions from x squared plus 9. And again, there's the fundamental theorem of algebra showing up again. That x squared plus 9 is contributing 2 solutions. All right, number 3 is 6th degree polynomial, number and type of roots for this polynomial. All right, okay, I'm seeing right there, I'm seeing 2 single roots. Okay, so if I've got 2 single roots, that leaves 4 roots unaccounted for, so that's going to be 4 imaginary roots. And by imaginary in this context, I mean non-real complex. Okay, but there are 2 single roots, 4 imaginary roots. That does add up to 6 degrees. That's the reason I chose 4. Okay. I think one thing I didn't point out in the video that I'm hoping you're noticing is that there's always an even number of imaginary roots. Okay, but again, more on that next time. Okay, figure it right showing the graph of a polynomial p of x. What's the lowest possible degree of p? I would say, based on these 2 relative extrema, degree 3. So 2 extrema. Okay, is it possible for the degree of p to be 4? No, I think because I can tell it's an odd degree because of the end behavior. As x approaches positive infinity, y is approaching positive infinity. But as x approaches negative infinity, y is approaching negative infinity, and a 4th degree polynomial can't do that. So that would be my reason why. If p is degree 3, how many complex roots does p have? Well, I can see 1 visible x-intercept, so that's 1 real root. And it's going to be a single root because the graph is passing through confidently. So if that's the case, then there's going to be 2 non-real complex roots is probably what I meant to ask. I wasn't really thinking about the fine print when I wrote this, but 2 imaginary roots. Because really all roots are complex roots, because all numbers are complex numbers. Would it be possible for p to only have real roots? Give a reason for my answer. Okay, I don't think so. You can write whatever you want on this. What I'm going to point out is that, if it was a triple root, we'd see the graph hesitating as it passed through the x-axis. Okay, but there's only 1 x-intercept, and the degree is at least 3. Okay, it's not degree 1 because it's curved, right? It's got these 2 turning around spots. But I'm only seeing 1 x-intercept, so there's gotta be imaginary roots. Okay, it could be like degree 5 or something, or degree 7, and there's just like a whole bunch of imaginary roots that we're not seeing. But that's not what they said. Okay, now we're going to sketch the graph of this polynomial and describe the number and type of roots. We're going to start by factoring this thing. We're going to say, all right, what's common to the first 2? That would be an x squared times x minus 2. And then what's common to the second one? That 4, so I'd say factor out the 4 times x minus 2. Okay. That's factoring f of x. And then I'm going to factor out that x minus 2 and x squared plus 4. Okay, so my number and type of roots is going to be one real root. That's that x-intercept at x equals negative 2. And this is going to give me two imaginary roots. But if I was to sketch the graph, I don't really know. We could say that maybe, it goes like that. It's third-degree polynomial with positive leading coefficient, so I know that that's the end behavior. I don't really know if it turns around or not. I mean, I kind of suspect that it does, but I'm not certain about that. What I would know in this case is that the x-coordinate here would be x equals positive 2. And that kind of makes sense, right? Because if I went in and I put that y-axis, like right through there, I would see that the y-intercept would be negative, which I can see from that negative 8. Okay, let's keep moving. So number 9, sketch the graph of g of x equals negative x cubed. I just had to make sure that one wasn't negative. Plus 9x squared minus 27x plus 27. Describe the number and type of roots. All right. Well, I'm going to factor this one just the same. So but I don't like to factor with a negative leading coefficient, so I'm just going to kind of factor out the negative in front. So negative and also an x squared to the first two terms. And I'd be multiplying by an x and a minus 9. Okay. Then what's common to the next one? That would be a negative 27, right? This is, hold on, this is messed up. This is not something I can group and factor. I feel like it's supposed to be 3x plus 27, minus 3x plus 27. Yeah, I'm not totally sure. I mean, pardon me if there was something I'm missing with this example, but I'm going to just change it to minus 3x plus 27 because, yeah, I'm not really seeing. I think this is just supposed to be group and factor. And yeah, then I'm going to factor out a negative 3 from there, and I'd get an x and a minus 9. Yeah, this looks more like it. So I'd end up with I'm going to factor out the negative and the x minus 9, and then I'd be left with a positive x squared and a positive 3, right? And so, yeah, this seems right. Okay, x minus 9 is going to give me one x-intercept at x equals 9, and x squared plus 3. That's not going to give me any real x-intercept. It's going to give me two imaginary solutions. Okay, so I've got one real root and two imaginary, which is just what I had in the other one. Yeah, I guess the difference is the leading coefficient. Okay, so a third-degree polynomial with a negative leading coefficient, and we don't know if it's going to, I mean, that's a single root. We don't know if it's going to be, like that and do its turnaround, if it's going to turn around there, or maybe it could be going to do that, right? We don't have the tools to determine that yet. We're going to say that's at x equals 9, but I think that's enough for that problem. Okay, right, the fourth-degree polynomial that has zeros. Okay, I forgot I put this on here. Okay, I'm going to just say I'm going to work this one using facts that you're going to learn in the next lesson. So, this is obviously not going to be on the quiz next time or anything like that. What was I going to say about this? Yeah, if you're not interested in this, just move on, but you're going to need to know how to do this eventually anyway. So you might as well just, watch me do this. All right, so if x equals 2i is a root of this polynomial, then x equals negative 2i is also going to be a root of the polynomial. Okay, so that means that I need x minus 2, x minus 3, x minus 2i, and x minus negative 2i. And I need to just multiply this all out. Okay, I'm going to do the first two together, x squared minus 5x plus 6. And then the second two together, x squared plus 4. Yeah, that's what's going to happen. And then I'm going to, and if you need to do, multiply it all out, x times x plus 2x times I, or 2ix minus 2ix, then minus 4i squared becomes positive 4. You can do that, no shame in that. But then I'm going to multiply this all together. Now, I don't think I'm going to do the box. I'm just going to distribute the x squared onto this whole thing, and then I'm going to distribute the 4 onto the whole thing, kind of line everything up, and then add the way I learned how. So x squared times x squared is x to the 4, minus 5x times x squared would be x to the 3, plus 6 times x squared. And then I'm going to multiply in the 4, so it would be 4x squared, and just seemed off somehow. 4 times negative 5x is negative 20x, and 4 times 6 is 24. Add this all together, and I didn't even think about this. I really should have some like leading coefficient out here. So this is going to be a times x to the 4 minus 5x to the 3 plus 10x to the 2 minus 20x plus 24. And a needs to equal 5 because of that leading coefficient business here. Yeah, right there. All right, so a is going to be 5. And let's say, all right, 5 times x to the 4 is 5x to the 4. Actually, let me just write it in like that. Then I'll re-emphasize it. 5x to the 4 minus 25x to the 3 plus 50x to the 2 minus 100x. 24 times 5, well, that would be 100, plus 4 times 5 is 120. And also, multiplying like 5 is kind of like dividing by 2 in some sense, so something to think about. Okay, and that would be a 4-3 polynomial with those zeros and has a leading coefficient of 5. With real coefficients or rational coefficients. What's the least number of zeros a polynomial can have when 2 of the zeros are root 5 and 3 minus I? Write the polynomial in standard form. Okay, yeah, this one's going to be a lot. All right, again, this is using facts that you don't really have yet and are not going to be on the quiz next time, but are going to be on the homework next time, so I guess I'm just showing you now. If x equals positive square root 5 is a root, x equals negative square root of 5 is going to be a root as well. Polynomial with rational coefficients. Okay. If we didn't have to have rational or real coefficients, then we could just, x minus root 5 and x minus 3 minus I, multiply it all out. It'd be really ugly, but we'd have something. But then, what I was saying in the last problem, if x equals 3 minus I is a root, then x equals 3 plus I is also, these are also roots. So I just got to get to work in here. So it's going to be like x minus square root 5, x minus negative square root of 5, multiplied by x minus 3 plus I would be x minus 3 minus I, times x minus 3 plus I, if I was subtracting x minus 3 minus I in parentheses. And I'm going to just multiply this all out. So this is going to give me x squared minus 5. And then this is going to give me, let's see, x squared minus 6x. Okay. I better ought to do this out for you. Especially since, yeah, to this point you have not learned about this yet. Okay, just watch me do this. It's very similar to what happened with the similar theorem in the last unit. All the stuff that's not real just cancels off. Right, see that negative 3i and positive 3i, the ix and the negative ix. Negative I times positive I is negative I squared, which is negative 1. Okay, so negative 1, that's positive 1. And so I've got x squared plus 10 minus 6x. So x squared minus 6x plus 10. And now I'm going to just multiply that all out. Probably going to clear out this box multiplication because you saw it happen. And if you need to see it again, you could rewind. And I'm going, okay, x squared times x squared, I'm distributing the x squared first. X to the 4 minus 6x to the third plus 10x to the 2. And when I distribute the negative 5, I'll have negative 5x squared, positive 30x, and negative 50. Okay, so the least number of zeros with rational coefficients would be 4. Okay, and then that means it's going to be a fourth degree polynomial, and we're about to write it in standard form: x to the 4 minus 6x to the 3 plus 5x to the 2. That's going to be frustrating. Alright, hope it stays, but 6x to the 3, positive 5x to the 2, positive 30x, and negative 50. There we go. Alright, so that's my standard form polynomial. I'm not sure what was happening there. Alright, now we're going to do some of these. Give a sketch of the graph of a polynomial that fits the criteria. Okay, by positive zeros and negative zeros, we just mean like to the left and right of the y-axis. So maybe I'll just draw the y-axis right here. And I'll sketch my graph in red. Okay, so 2 positives, 1 negative, and 2 imaginary. Okay, so I should probably say, okay, I've got 3 real and 2 imaginary. That's going to be degree 5. And nobody said anything about what the negative, or but whether the leading coefficient was negative or positive, so I mean, it doesn't really matter. This is going to be a positive leading coefficient. It can have that last wiggle in there. It could not. It doesn't really matter. It's up to your judgment. It's your graph you're drawing. So 1 positive 0 with multiplicity 2. I'll draw this a little more in the middle. And 2 imaginary zeros. Okay, well, I guess they're implying there's no negative roots. And 2 imaginary, maybe I'll make this one have a negative leading coefficient. So I've got 4 roots. Wait, yeah, maybe. Yeah, it could look like that. We really don't know what the behavior of the graph is off of that. I just kind of want to emphasize that uncertainty there. Okay, that's the 0 with multiplicity 2, and then 2 imaginary zeros means I'm not, not running them into the x-axis to account for it, but it is still 4th degree. So it could look something like that. 1 real 0 with multiplicity 3, 2 imaginary zeros, and a negative leading coefficient. 0 and a negative leading coefficient. Okay, so multiplicity 3 plus 2 imaginary zeros, that's going to be degree 5 again. So degree 5 with a negative leading coefficient means it's going to come from above and then go down. So it's hesitating. That was my triple root, and maybe it turned around once again. That was right there. And yeah, that fits potentially. All right, this explain why it can't problem. I like these. Okay, these are always kind of a puzzle. And then we're going to learn more facts about polynomials in the next lesson, and then kind of have to juggle all of them together, and that's really something that you have to do later on in subsequent math classes. So it's good practice. So Q is a 5th degree polynomial with a negative leading coefficient. Explain why Q can't have 2 positives, 1 negative, and no imaginary. Oh, well, it's a 5th degree polynomial, right? So I got to add up to 5 roots. Okay. 2 positive zeros, 1 negative 0, and no imaginary. And by positive, 2 positive, we mean like distinct positive roots. If we have, that's a total of 3, but I need 5. Okay. If one of these had, if one of the real roots had multiplicity 2, no, I think I need 2 of them to have multiplicity 2. And then I'd have degree 5. Or otherwise I need like 2 imaginary roots or something. Alright, suppose P is a 4th degree polynomial. Explain why P can't have 2 positives, 1 negative, and 1 imaginary. Ah, you don't know this yet. That's too bad. This would have been a much better question for the next homework. Imaginary roots, they come in conjugate pairs. Let me just make sure I'm recording homework 7.2 right now. Yeah, that's a shame. I just feel like some of these problems I meant to put on the next homework, but it's all good. I'm going to say imaginary roots come in pairs. As in, like, there's only ever 2 or 4 or 6 or 8 of them. There's never 1 or 3. Can't have that. Okay, let's give a sketch of a 3rd degree polynomial with 2 imaginary roots. Okay, we've done this quite a few times, but, something like that. That would work. Yeah, I'd say that'll work for me. Fourth degree polynomial with no imaginary roots. Okay, you could make it be like, okay, double root and two singles, or you could say a triple root and a single, or you could do the old-fashioned 1, 2, 3, 4 single roots. Okay, no matter what, it's fine. Just, think about the possibilities and give yourself a sketch. Find the values of x that make the equation true. All right, this is the last page. Okay, good. Homework with a lot of variety on it. Okay, so I'm going to go up here and I'm going to say, all right, directly solve it. This one, 3x squared equals negative 48. Divide by 3. Take the square root of both sides. Don't forget the plus minus. Okay, the square root of 16, we know that's 4. So x equals positive or negative 4i, so it'll be x equals 4i, x equals negative 4i, and we're good. Okay, this next one, no, nothing multiplies to 6 and adds to 2, so I'm going to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c. Okay, yeah, 2 times 2 minus 4 times 1 times 6, all over 2a. All right, so this is negative 1 plus or minus. All right, root 12. I need to probably do a little bit of square root of negative 12 equals square root of 4, square root of 3, square root of negative 1. So 2 root 3i, if I divide by 2, I just have 1 root 3i. So my solutions, yeah, these are both second degree, so I would expect to have 2 roots. All right, this is third degree, so I should expect to have 3 roots, right? So I go back over here and I say factor. Yeah, let's factor here. I'm going to take out an x. I feel like this is another one of those, it looks super factorable, but it's not. Okay, you want it to be. If this was x squared minus 4x minus 5, we'd be in business. But this needs to be, it would need to be a minus 6 or a plus 6 in order for this to be factorable. And it's not, so all right, I'd say this gives me x equals 0. Over here, I need to do some quadratic formula work. Negative b is positive 4 plus or minus the square root of b squared minus 4ac all over 2a. I feel like we've solved this one a couple of times. This is a real nice one. 4 plus or minus the square root of negative 4 divided by 2. That's going to be 4 over 2 plus or minus square root of negative 4 is going to be 2i. So 2i divided by 2 is just 1i. So x equals 2 plus I, x equals 2 minus I. These are my 3 roots to my degree 3 polynomial. And then this one then kindly factored it for me. So either 7x equals 0, and that'll be x equals 0. So I'll start my list here. Or maybe x minus 8 equals 0, and that will give me x equals 8. Or maybe x squared plus 1 equals 0. And that would mean x squared equaled negative, no, that's not true. X squared equals negative 1, and I take the square root of both sides, plus or minus the square root of negative 1. Okay, we know that's called I. Okay, so that's going to give us our last two solutions, and that's going to be x equals positive I and x equals negative I. Wait, whoops. All right, there you go. That's going to be all the examples for this homework. Yeah, thanks for watching.